Okay, so this is a set of notes on Cauchy-Schwarz, the triangle inequality, and the Pythagorean theorem. Okay, so Cauchy-Schwarz basically says that if I have two vectors, u and v, and they are in Rn, then the absolute value of the dot product of u and v is less than or equal to the magnitude of u times the magnitude of v. Okay, so there's a trivial case for this, so let's start building the proof. The trivial case is if u or v is the zero vector, then clearly the dot product of u and v is 0. Likewise, the magnitude, the product of the magnitudes would also be 0, so we clearly get equality there, and that would make this true. So let's look at the non-trivial case. So this would be where u or v, or u and v, are both not 0, right? So u and v are not equal to the 0 vector. Okay, so what we're going to do here is we're going to do some letting. Let A be the dot product of u with itself. Let B be 2 times the dot product of u times v. And we're going to let C be the dot product of v with itself. Okay, so we're going to consider something. We're going to consider the vector t times u plus v. Okay, so we're going to take t times u plus v dot t times u plus v. Okay, and in the end there, we're going to say we know that this has to be greater than or equal to 0 because this is the same as the magnitude squared, and the magnitude always has to be non-negative. Okay, so a little bit of algebra here, and you're going to get t squared times u dot u plus 2t times u dot v plus v dot v is e greater than or equal to 0. So this is the result of binomial multiplication of vectors and the distributive property. You can try that out for yourself and see that it works. So this is going to give me at squared plus bt plus c is greater than or equal to 0. This is a quadratic, and this is a quadratic of reals, okay? So, because a is a real constant, it's a dot product. B is a real constant, it's 2 times a dot product. C is a real constant, also a dot product. So this is a parabola. Oh, this should be, oh, that's not right. Should be 2b, should be bt, not b squared, right? There we go. So this is a parabola. And this parabola is always greater than or equal to 0. So at most, it's going to touch the x-axis 1 time, which means that its discriminant, b squared minus 4ac, must be less than or equal to 0, right? Because this thing is only going to have at most 1 real root, if at most it's only going to touch the x-axis 1 time. This means that b squared is less than or equal to 4ac. Now, let's get some space up top here again. Let's kind of carve some of this out. There we go. Get rid of that. And let's unpack what that was. B was 2, so this is going to be 4 u dot v squared, right, is less than or equal to 4 times a, which is u dot u, times c, which is v dot v. So lo and behold, those cancel. This squared, well, that happens to be let's leave that alone for a second here. U dot v squared, right, is less than or equal to, what do we get here? This is the same as the magnitude of u squared times the magnitude of v squared. So if I take the square root of both sides, this is the absolute value of u dot v is less than or equal to the magnitude of u times the magnitude of v. And lo and behold, we have proven Cauchy-Schwarz. All right, so from Cauchy-Schwarz, we're going to get the triangle inequality. Okay, so let's work on the triangle inequality. Okay, so the triangle inequality says that if I have a vector u and a vector v, and they're in Rn, then the magnitude of u plus v is less than or equal to the magnitude of u plus the magnitude of v. Okay, this can also be called a statement of subadditivity, but most cases for Rn, we're just going to call it a triangle inequality. All right, so proving this, let's start from the left, but we're going to square it. So we're going to take the magnitude of u plus v squared, which is u plus v, dotted with itself, right? So this becomes u dot u plus 2 u dot v plus v dot v, right? So this looks vaguely familiar. Okay, so this is the magnitude of u squared plus 2 times u dot v plus the magnitude of v squared. Okay, so this has to be, this could be negative, the middle term. So this has to be less than 2 times the absolute value of u dot v, which should suddenly ring bells that we put an absolute value in there, because now by Cauchy-Schwarz, this has to be less than u squared plus 2 times the magnitude of u times the magnitude of v plus the magnitude of v squared, which is equal to the magnitude of u plus the magnitude of v squared, because it's a binomial square. And then you just take the square root of both sides, which gets me u plus v has to be less than or equal to the magnitude of u plus the magnitude of v. And through Cauchy-Schwarz, so Cauchy-Schwarz is right here. This is the Cauchy-Schwarz step. We have proven the triangle inequality. Now, the last one here, and I'm not going to erase the triangle inequality proof here, is the Pythagorean theorem. And the Pythagorean theorem says that if u dot v is equal to 0, in other words, u is perpendicular to or orthogonal to v, then we can say that the magnitude of u plus v squared is no longer less than or equal to, but it's specifically equal to u squared plus v squared. So if the vectors are orthogonal, then the square of the hypotenuse is equal to the square of the two legs. Okay, so here's the argument. Let's take a look at the triangle inequality proof. We're still starting at this point. We go to here, but you'll note right there is a 2u dot v. So that gets pulled out, which gets pulled out here, which leaves me here, which says that u plus v squared is equal to, because this is all equality so far, the magnitude of u squared plus the magnitude of v squared. And so Pythagoras is like a special case of the triangle inequality where the cross term happens to work out to be 0, and I can get to this equality much faster. Okay, so there you go. There's Cauchy-Schwarz, the triangle inequality, and the Pythagorean theorem.